Okay, so it's recording this whole thing. Everything will be written on this computer. So the whole lecture will be up. I'm assuming it comes out okay. I'll post it up on YouTube so you'll be able to watch it that way. So the way encryption works, long ago, if you had a message that you wanted to send, like hello, the first ever encryption scheme was something called the Caesar shift, which was a very simple encryption scheme. Basically, the way it worked is you took the word hello and you chose a number like 2, and you added you moved each letter up in the alphabet by 2 positions. So hello became JGNNQ, and you would send that to your person. And if somebody intercepted the message and didn't know how it got encrypted, they wouldn't be able to do anything with this gibberish. This was not a very secure system because all you had to do was shift back once, twice, a bunch of times, and until it became words that made sense. So this encryption scheme was the first encryption scheme. It's very insecure. There's only 26 ways something could have been encrypted, so you could test the 26 reverse ways, and you've got yourself. It's not secure enough. But back in Caesar's time, that was your original encryption scheme. Later on, they invented something called a substitution cipher. And a substitution cipher is where you have the word hello, and you have a key. A key is a list of the 26 letters of the alphabet, and what letter each letter is going to get converted into. And it's not just that A becomes C and B becomes D, that everything's shifted, but it's a random scrambling of the 26 letters of the alphabet. So maybe hello in one of the schemes becomes RMAAX, and you can shift all you want. You're not going to find hello that way because it wasn't made by shifting. It was a scrambling of the 26 letters. Well, now there's 26 factorial, which is a gigantic number, ways that you could scramble up the 26 letters of the alphabet to make your key. So nobody can break this by just testing all the possibilities because it would take too long. However, in time, the code breakers did figure out that if you have enough text created with one of these substitution ciphers, you could just look at the most frequent letters. So if an X comes up a lot of times, you can assume that that letter is probably an E, because E is the most common letter in the English alphabet. And in doing this, they were able to do something called frequency analysis, where the most common letters in your encrypted text probably correspond to the most common letters in the original text. And then with a little bit of trial and error, they're able to crack that one too. So substitution cipher isn't really used anymore. And they came with other really clever ideas. For instance, rather than turn the letters into other letters, turn the letters into numbers and make the numbers from 1 to 100. And if 20% of the actual letters are the letter E, then give E 20 different numbers in your code. And if 1% of the letters are Z, give Z one number. And then if someone tries to do frequency distribution on your encrypted text, they're not going to learn anything because every number is going to come up with the same frequency because they cheated in that way. That also got broken. They found pairs of numbers that came up frequently and were able to crack that also. So encryption is basically a game between code makers and code breakers. Code makers come up with a code, a way of encrypting. Code breakers break it. And then the code makers have to come up with a better scheme for encrypting, and the code breakers break that one. And it goes back and forth. Right now, the code makers, it's in the code breakers' court right now, because the code makers have something called RSA encryption, which is the most common encryption used. And code breakers have not broken it yet, and I'll explain why that is and what it would take to break that. Some of your parents maybe don't like to use the internet to put their credit card number in, because they say, well, who knows, I typed in my credit card number, who could be like tapping my line or doing something. But in reality, it's a lot more secure to put your credit card number into the internet and hit send than it is to use your credit card in a restaurant where you give it to a waiter, and the waiter can walk with it, and any number of people could look at it, including the waiter, but all different people can look at it while he's putting it in and even look at the back to see stuff. So I'll tell you why RSA encryption is secure also. The math that RSA encryption is based on is called number theory. And number theory is a subject that's based a lot on something you learned as a young child. When you divide 5 into 13, you get 2, and you get remainder 3. That R that you learned when you were maybe in 3rd grade or 4th grade with division, later on in your math career, they told you don't do R3 anymore. You do decimal remainder or fraction remainder. And R, big R, is just for little kids. We don't do that anymore. But actually, in higher math, that remainder becomes very important. And mathematicians actually would say the fact that you get remainder 3 when you divide 13 by 5, they might say it this way: 13 triple equal sign. That means is congruent to 3 parentheses mod 5. That's a fancy way of saying that when you divide 13 by 5, you get remainder 3. So to make sure you have this concept, what if I said this? 27 is congruent to what? Mod 5. And I'll get a volunteer for that. 27 is congruent, yes? It is 2. That's right. Because 27 divided by 5 is 5, remainder 2. A more difficult question is this. Question mark is congruent to 2 mod 5. And this is harder because it's ambiguous. There's more than one answer. It could be 27. 27 does equal, when you divide 27 by 5, you do get remainder 2. But there are other numbers that you could divide by 5 and get remainder 2. I'll just get a volunteer for a few, yes? 7. Can you name a few more?
We do 7 plus 5x or x.
Okay, so anything, or 2 plus 5x, that's right. So 7 would work, 27 would work, 12 would work, 32 would work. Actually, anything that ends in a 2 or a 7 would work.
Except for 2 itself.
Oh, it's funny you should say that. 2 itself actually does work, because when you divide 2 into 2, you get, when you divide by 5, though. 2 divided by 5 is 0, remainder 2. So it actually even works for the number 2. So this is a concept that this idea of mod is a concept that you need to understand. Yes, you actually are allowed to, you are allowed to even use negative numbers. The official definition of mod is actually not what's the remainder when you divide by this, but the official remainder is 2 things are congruent if when you subtract them, 13 minus 3 equals 10, and 10 is evenly divisible by 5. That's what makes 2 things congruent. But most nowadays, most people for basic number theory, most people just think of this number as having to be the remainder, and generally this number being bigger than the mod number. Okay, the next idea is something called modular exponentiation. And that basically means that if you want to raise something like 7 to the 257th power, and you want to mod it by 5. Well, 7 to the 257th power is a very large number. And if you type it into your calculator, it might crash the calculator. And certainly if I made it not 257, but 10,000 or a million, it would be very hard. If I made that number really big, like, so there's 2 complications. The number gets a large number. But a second complication is when that exponent gets giant, meaning like a number with 100 digits in it, not only would the number be so big to be practical, but it would actually take too long. A computer, we think of computers as doing stuff so fast And computers can do calculations pretty fast, you know, a million calculations, a billion calculations. But when you start trying to do 10 to the 100th power number of calculations, the computer can't do it. It's not fast enough. It would take years and years for it to do. But there are some shortcuts, not only for how much time it takes to answer this question, but also a way of not getting the number to be so big. And basically, as they start multiplying, going along, as the number gets big, they divide by 5, take the remainder at that time, and just keep going. So the number actually never gets big. But they also have figured out the speed issue. I have here a program. Oh, I see. I'm going to need to. It's a bit challenging, actually. I just realized. Okay, let me just go this way. So I have a program that I have here that says modular exponentiation as choice number 1. And I could do this question. I could say, what is 7 raised to the 257th power? And what happens when I mod that by 5? And it will answer the question really fast. And it's not doing what you'd probably expect. It's not actually raising 7 to the 257th power, dividing it by 5, and taking the remainder. It has some clever things, but I will tell you that this program is very, very fast, even if I use gigantic numbers. Even if my number, my exponent, had 200 digits in it, this program would work almost instantaneously. So it is possible to answer questions like this very quickly on a computer. The reason this is all important is because the encryption scheme known as RSA, RSA, by the way, is named after 3 professors at MIT. I think it was Rivas, Shamir, and Edelman invented this idea in the 1970s. RSA basically says there's 2 people. We have Bob and Alice. In cryptography, they usually call the people Alice and Bob for A and B. And sometimes there's a third person named Eve, which is for eavesdropper. If somebody's listening in, we have Eve, Alice, Bob, and Eve sometimes are the 3 people they talk about a lot. So let's say Bob wants to send a message to Alice. He wants to send a message. And these messages have to be numbers. But let's say Bob wants to send a message that's a letter, so it's the letter Q. He wants to send her that message. Make it simple for now. RSA only works with numbers, so Bob first can turn the letter Q into a number, and one way of doing that is just seeing what position the letter Q is in the alphabet, the 17th letter of the alphabet. Now, Bob's not going to send the number 17 to Alice because that's not encrypted. He has to first convert 17 into another number and send that number to Alice. And Alice somehow knows how to take that number and how to convert it back into the number 17, how to decrypt it. Well, in order for Bob to do this, Bob needs to know something called Alice's public key. The public key is is instructions for what to do with that number 17 before you send it over. Now, this happens on your computer before you send it. So it's not like you send the number 17, it gets converted and sent to Alice. Your computer first changes it to whatever it's going to become, and then that number gets sent over. So the eavesdropper never sees the number 17. So Alice's public key in this case is a sequence of 2 numbers, 7, 143. Alice created this, and I'm going to teach you how she would have come up with this public key. And she tells Bob, listen, here's what you do. Here's how you encrypt. This is what you do. And everyone actually knows Alice's public key. That's why it's public. So even Eve the eavesdropper knows Alice's public key. What you do with this 7143 is this. The way you use the public key is, and C is what we call the encrypted text or ciphertext. C is equal to the message raised to, this first number is known as E for encryption number, and the second number is known as N. So the way you encrypt is you raise the initial message to the E power and then mod it by 100 by N, that is, by N. So in this example, the ciphertext is going to be whatever 17 to the 7th power mod 143 is. And I could do it. I should have said 17 to the 7th power mod 143. And that's the message that he sends. Number 30. And that's how RSA encryption works. Now, why this works or why this is secure is not clear yet to you because I haven't explained all the math behind it. But I'm telling you that's all RSA encryption is. It's raising the message that you're trying to send to whatever the first number in public key is, and then modding it by whatever the second number in public key is, and that's the message that gets sent out. That's the ciphertext. So 30 gets sent to Alice. Now, I'm going to tell you that undoing the 30, figuring out what went in to make 30 come out, is difficult if the numbers were a lot bigger. For this example, it's very easy. All someone who eavesdropped would have to do, since they know how the 30 came about, they could just test every number from 0 to 143 and see which one makes 30 come out. And I will tell you that it would only be one answer in this. If you put a number in between 1 and 143, it has to be less than 143 because that's what you're modding by. Each number that you put in makes a unique number come out. So anyone who's in this example, you can just test every number from 1 to 143. You get to 17, plug it in, 30 comes out, and you're done. You decrypt it. But if that number was not 143, but was a number with 200 digits in it, you would not have the option of testing every possibility. Let me tell you what Alice does to decrypt it. Alice, and only Alice, knows something called Alice's, I'll call it private key. Sometimes called the secret key. Alice's private key is 103, 143. I'll explain how I got these numbers. That's the goal of this whole lecture. But I'm telling you, Alice's private key is 103, 143. Notice how the 143 is the same as the other 143. The only thing that's different is this number. That number in RSA encryption world is known as the number D. Alice can retrieve or can decrypt this message and get it back to the original one by simply M should be C to the D power mod N, which in this case is 30, that's the number that he sent, to the 103rd power mod 143, just to make sure that works. So according to this, at least I'm claiming that if I take the number 30, the message that was sent to me, and I raise it to the 103rd power, and I mod that by 143, it comes back to 17, like it was supposed to. So the encryption key, everyone knows, you just raise it to the power, mod it, that's what gets sent. But somehow, only Alice knows that to undo this function, 103 is the magic number that will undo the function. that I could raise the encrypted message to. And I will tell you why that is today. That's the goal. And we're actually doing pretty good on time, so I'll definitely be able to teach you this in the next 35 minutes. But that's the basic idea. Now, this entire RSA encryption is based on something called Fermat's little theorem. Fermat was a French mathematician in the 1600s who made a lot of theorems about number theory. A lot of them were just conjectures. And later on, someone named Euler proved most of his conjectures and even disproved some of them. Euler was about 100 years later. Fermat's most famous theorem is known as Fermat's last theorem. Just on the side, Fermat's last theorem is different from Fermat's little theorem, very different. Fermat's last theorem says that while there are a lot of Pythagorean triples, if you try to change the number, the exponent, to a 3, and they have to be 3 different whole numbers, 3 different positive integers, that you never find one. You never find a Pythagorean triple where something cubed plus something cubed equals something else cubed, or something to the 4th power plus something else to the 4th power equals something else to the 4th power, or anything past 2. 2 is the last exponent that works. That's what Fermat's last theorem. That was not proved for over 300 years. It just got proved maybe less than 20 years ago. Fermat's little theorem is much simpler and has nothing to do with exponents. But I just thought I'd let you know, because a lot of people heard Fermat and instantly think Fermat's last theorem. But Fermat's little theorem is, well, it says this. It says that if you take a number and you raise it to the p minus 1 power, where p is prime, and you mod it by p, which is prime, you always get the number 1. That's what Fermat's little theorem says. So, for instance, if p equals 13, this claims that 7 to the 12th should equal 1 if I mod it by 13. That's what Fermat's little theorem says. It's a theorem about what kind of remainder you get when you raise something to a power. And I'll verify it for this example. So Fermat's little theorem again says that if you have a prime number and you raise anything to 1 less than that prime number, and you mod it by that prime number, you will always get the number 1. I'll do it for this. 7 to the 12th mod 13. So according to this, 7, sorry, not choice 7, but 7 to the 12th mod 13, and it does equal 1. And that's what Fermat's little theorem says. Now, when Fermat invented the little theorem, it was not considered very practical for real life. And we learn a lot in math, you know, this thing is used in physics, and this thing is used in astronomy, and this thing is used in engineering. And a lot of teachers use that to convince the students, you know, this is worth hearing. The truth is, a lot of math does not really have practical application, and I think that's okay. Some of the more interesting math, more fun, pattern finding, and things like that don't have practical applications, just the way drawing a painting doesn't have a practical, just draw, you know, signs for people to know how to get from place to place or whatever. Things don't have to be practical. Some of the best math is not practical. When Fermat's little theorem was invented, it had no practical value whatsoever, and he didn't mind because he was a pure mathematician and versus an applied mathematician. He was really just trying to unlock the mysteries of numbers. Little did he know that 400 years later, when computers got invented, Fermat's little theorem would be used billions of times a day as the basis of an encryption scheme that remains the most powerful encryption scheme that we have. So it's ironic. He had no So some of these things may have some application later on, even the things we're learning, but not everything has practical applications yet, and some things may never have practical applications. Here's something that has no practical applications whatsoever, and probably never will. Fermat's last theorem. There's no practical applications of that as far as I know, and maybe there never will be. Yet it was the greatest mystery in math for 400 years. Here's a bit of a corollary to Fermat's little theorem. If I raise 7 not to the 12th power, but to the 24th power, or to the 36th power, I would also get 1. And that's basically because 7 to the 24th is the same thing as 7 to the 12th to the 2nd power. So if 7 to the 12th became 1, this is in mod 13. So not only that a to the p minus 1 always equals 1, but I'll go more general and say a to the anything times p minus 1 will equal 1 mod p. So if I were to go 7 not to the 12th, but to the 60th power, which is 12 times 5, mod 13, I would also get 1. So in this mod world, the whole rule of raising a power to a power still works. So that usually we go in this other direction. Usually we say 7 to the 12th to the 2nd becomes 7 to the 24th. But you go the other direction also. If you want to get 7 to the 24th, and you know what 7 to the 12th is, you can split it up in the other direction. And I'll go one more corollary for you, and then we'll be just about ready for the math we need for why RSA encryption works and how you can make your own public and private key pairs. If, instead of this, I add 1, it's going to become a. And the reason why that is because going in the opposite direction, well, I'll just say this, a to the 1 times a to the whatever is a to the m plus 1. And that works in the opposite direction also. If you ever see something with a plus 1, you can split it up. So if this here without the plus 1 was equal to 1, and then if I multiply both sides by a, the left side would get a plus 1 on that exponent, whereas the right side would become a. So that's sort of an extra thing that might take a little minute to digest. I hope this explanation helps you. This definitely becomes that, which means that this can go backwards, which means that basically I suppose I could say this one other way. I suppose I could say if I have a to the m equals something, just make up, I'm running out of no. And if I multiply both sides by a, no, when I say if a to the m equals 1, and I multiply both sides by a, the left side becomes a to the m plus 1, and the right side becomes a. That's the basic idea. I'm recording this, and I'm hoping to put it up onto YouTube. I didn't do a sound check. Hopefully it's okay. Well, that is Fermat's little theorem. It doesn't seem very useful, and it was not useful till recently, but just to give you a sort of heads up of where this is going. In encryption, we start with something, and eventually we end with that same thing, and that's part of why this is related to encryption. We start with some message that needs to be encrypted. It gets encrypted, eventually it gets decrypted, ends up back at its original thing. Now, I mentioned Euler, who was 100 years after Fermat, 1700s. Euler was my favorite mathematician. He wrote more than any other mathematician that ever lived, and a lot of the stuff he wrote about was stuff that people had not been writing about for a while because they thought it was too easy. But he would take something that seemed easy and go so into it and show all the little details of it suddenly showed there's a lot more to it than people realize. So when Euler discovered Fermat's number theory, he said, wow, there's a lot in here that hasn't been explored. And number theory was, no one cared about number theory. Number theory was basically studied by two people ever, Diophantus in like the year 800, and Fermat in the year 1600, and then it was forgotten about for like 100 years. No one really cared about it. Euler said, I think there's something in here that I can work with. Euler created something that's now known as the Euler-Fermat theorem. Remember, Fermat's little theorem says that a to the p minus 1 is always equal to 1 by mod by p. But what if p is not prime? It doesn't work anymore. Like, for instance, if I want to know, let's say p equals 15, which isn't prime, and I try to do 7 to the 15 minus 1 mod 15. Let's see if it becomes 1. Which I haven't checked this one. I hope it doesn't, because it would not prove, it would make my point seem like it wasn't true. But let's see. 7 to the 14. I hope this doesn't work. I hope it doesn't say 1. It didn't. Good. Sometimes it does work, but the point is it doesn't always work. So Fermat's little theorem does not work for composite numbers. So Euler made a more general theorem that works for composite numbers, and this is the theorem that really gets used in RSA encryption. So I'll tell you about the Euler-Fermat the Euler-Fermat theorem. The Euler-Fermat theorem says that if the number is composite, and now we're going to call it n instead of p. He says the exponent is not going to be n minus 1 like it was for p minus 1 like it was for prime. If 14 is not the right number to make this always work. Instead, for the number 15, the number is going to be 8. And I'll just first show you an example to demonstrate that this actually 7 is not a good number. There's actually a couple of restrictions on here, but let's say 9 to the 8. Didn't work. Hold on a second. There's a couple of restrictions. Let me try prime number. Wait a second. Let me just try 2 first. Let me think for a second. What's going on? Oh no, of course. It's not 8. It's not the number. It's 7. Sorry about that. This number is not supposed to be 8. Wait a second. No, it's 5. It's 8. Yeah. Yeah. It's 8. So what's wrong with my? Hold on. Okay. Now there's a little bit of restriction on what number you can use. So 2 to the 8th to become 1, but 3 to the 8th mod 15 becomes 6, but it has to be relatively prime to 4 to the 8th mod 15. Does work. But
pick a number relatively prime to 15.
Oh, to 15, so not to 4.
So like 9 won't work.
I see. Okay, so there is a bit of a restriction on what number you could use, but in general, so let me just make a quick note here. This a value can't have a common factor with 15, so can't have common factor. There's not that many when this number is gigantic, hundreds of digits. There's very few bad numbers that sort of make this thing not work, but sorry about that. There's a little bit of a restriction. Okay, so that's what the Euler-Fermat theorem says, but where did this number 7 come from? Here it is. The number 7 is there because it is what's called nowadays, I don't think Euler called it this, but nowadays we say phi of 15 equals 7. All that means is that if you took all the numbers from 1 to 15, is 8? Oh, this thing's back to being 8. If you took all the numbers from 1 to 15, and you circled all the numbers that did not have a common factor with 15. So 2 would be okay, 3 wouldn't be okay, 4 would be okay, 5 wouldn't, 6 would be bad because it goes to a common factor of 3. 7's okay, 8's okay, 9's bad, 10 has a 5 in it, 11's okay, 12's bad because of the 3, 13's okay, 14's okay, 15's bad. And you count them. 1, 2, 3, 4, 5, 6, 7, 8. That's called Euler's phi function. It's the number of numbers less than that number that does not share a common factor with it. And the way I think of it sometimes is if you were to make fractions, 1 over 15, 2 over 15, 3 over 15, 4 over 15, 5 over 15, which of these fractions could not be reduced anymore? And what you'd be left with is 8 of them, because for 3 over 15 could be reduced. So you've actually experienced the whole idea of what's called relatively prime. Anytime you try to reduce fractions, why can't I reduce 7 over 15? They don't have a common factor. Why can't I reduce 6 over 15? Because 3 goes into both. So you actually had, even as a child, that when you reduce fractions in your mind, you like look at two numbers and say, they're not relatively prime. You're not saying those words, but that's what you're kind of saying. So now we have Euler's phi function. Here's what Euler's phi function is now, or here's Euler-Fermat theorem. Euler-Fermat theorem says that a to the phi of n will always equal 1 mod n. Like I mentioned before, there's a bit of a restriction on a, but in general, corollary to that is if I multiply that phi of n by something, don't worry about that, pay no attention to the man behind the curtain. So this basically means that it doesn't just have to be for, if n is 15, phi of n is 8, I could not only do 8, but I could do any multiple of 8 will work. So just to verify that, if instead I do 4 to the 80th power and mod it by 15, I also get 1, because I'm raising the power to a power, but 1 to a power is still 1. And for our purposes, here's our big second corollary. If I were to add 1 to this number, I would get back to A. This here is the key theorem that gets used in RSA encryption. So this means that if I take a number, like 4, and I raise it to 1 more than a multiple of 8, like 161, and I mod it by 15, I'll get back. What happened there? Oh yes, I'll get to 4, which is what I wanted to get. It will get me back to my original number. So the one thing you really want to get from today, even if you didn't follow everything up to now, is that this theorem is the big one, and it lets me get from my original back to my lets me get back there. Now here's how this applies to RSA encryption. Let's go back to Alice and Bob from before. You might remember the message Bob wanted to send to Alice was the number 17. Alice needs to make her public key to send to Bob and to anyone who wants to send her an encrypted message. She's going to make her public key and her private key, and she's going to send the public key out. So here is how Alice made her public/private key pair. And I'll also explain why this whole thing works. Been very good on time for this. The way Alice makes her public key is she starts by making up two primes. Make up two random primes. And Alice picked 11 and 13. So it starts with just two random prime numbers. The bigger, the better. So 100 digits is pretty good. You might say, how do I get a 100-digit prime? It's very easy to get a 100-digit prime with a computer. You can make up a random 100-digit number. And there's a way to check if a number is prime. It takes no time. However, to actually factor a number that's not prime takes hundreds of years. So you should know that it's important that factoring is one of those things that's very slow for computers. 200-digit composite number, a couple of years to factor on a computer. But you can actually create a prime number, ironically, and check if it is prime without, and it might say, no, it's not. And then you say, where's factor? It says, give me a year. But that's an ironic thing in math. Now you start with two random primes. Then you multiply those two primes together. And that 143 is the in that is part of Alice's public key and part of her private key. Now you say, okay, but what about the rest of her public key? We had her raising 7 was her D number. So get this, the E can also be randomly chosen. Now it doesn't have to be a prime, but it's safest if you make it a prime. So that Alice's public key was just basically completely made up. Literally, she just made up two random primes, multiplied them together. Got a third one, that was her e-value, and she sent it out. Here's my public key. And remember from before, Bob wanted to send the message 17 to Alice, so he knew what to do with this public key. He raised his number to the, this is the E number, to the E power, and modded it by 143. And out came the number 30, encrypted. Sends the number 30 over to her using her public key that she basically randomly created by making up two random primes, multiplying together. Third random prime became the e-value. Here's my public key. Encrypt and send it to me, and it's safe. Well, the question is, how is that safe? Well, it's going to come with how she encrypts it. When you see how she encrypts it, it will also explain why this is safe. Alice's private key. For Alice to get her private key, which incidentally has 143 here, the big question is, how did she know that her magic exponent for her to reverse this thing was 103? What's so special about the number 103? And how was she able to calculate it, but everyone else who knows her public key isn't able to figure out that number? The way she gets D, the way she knew it was 103 instead of some other thing, is Alice has to calculate out the equation ED is equal to 1 mod phi of n. In other words, for this example, E is 7, so she needs to figure out 7 times what will be 1 if I mod it by. Now, phi of 143, that seems pretty tricky. And if it's a really big number, how do I get it? Well, I'm going to tell you there's a shortcut for getting phi. Phi of a prime number is real easy. It's always one less, because every number is relatively prime to a prime number. That's a prime number. But 143 is not a prime number. It's a composite number that was calculated by multiplying two prime numbers together. Without getting into it right now, I'm going to tell you that phi of pq is going to be p minus 1 times q minus 1. Remember, phi of 15 was 8. 15 is 5 times 3. 5 minus 1 times 3 minus 1 is 4 times 2, which is 8. So there is a shortcut for calculating a phi of a composite number that's two primes multiplied together. So in this case, phi of 143 is 11 times 13, so it's 10 times 12, which is 120. So what Alice needs is a number that multiplied by 7 gives me remainder 1 when you divide by 120. Well, that seems hard. It actually can be done by hand fairly easily, but I will also tell you that that you could write a computer program that does it very fast. So it's called modular inverse. Kind of like when you multiply two numbers together, you get 1. That's an inverse. So the first number was 7. The second number, I guess I forgot how I wrote this. So that must be the mod 120, and it tells me 103. And in this program, everyone has this program, the modular inverse. So it also could have been done by trial and error, I suppose. Alice figures out that D is 103. Let me show you a little more about this 103. So what we're saying is that 17 raised to the 7th power, then raised to the 103rd power. Because remember, 7 was the original exponent. That's what encrypted it. Then she decrypted it by raising that to the 103rd power. Well, this becomes 17 to the 721. But 721 is 6 times 120 plus 1. The Euler-Fermat theorem says that if I mod this by 143, Euler-Fermat theorem says that 17 to the something times phi of 143 plus 1 should get me back to 17. So this number is the special number, so that this times this will be 1 more than phi of 143. 721 is the number. Probably went too fast on that, but that's the basic idea. It's all based on Euler-Fermat theorem. So the big question is now, if everybody knows that her public key is 7143, then everybody can factor 143 into 13 times 11, and then everybody can run the 7. Sorry. Everyone knows phi of 143 is 120, 10 times 12. So everyone who has the program for figuring out the 103 could just break this. And that's where RSA encryption comes in, because though everybody knows the 143, only Alice knows that it was 13 times 11. Anyone who can factor that big N number can figure out what P and Q are, can subtract 1 from each of them, multiply them together, can run that number through and get the secret key. Anyone who can factor. The RSA is only as secure as factoring is. So 143 is easy to factor, but you change that 143 into 200-digit, multiply 200-digit prime numbers together, they can't factor it. If they can't factor it, they can't get P and Q. If they can't get P and Q, they can't get phi of that giant number. If they can't get phi of that giant number, they can't use it to work out the D value, and they're stuck. So that's the gist of RSA encryption. I think I'll put up another example just so that you have another example for you. So let's say that the situation was someone's public key was 2755. And somebody wants to send the message. I'm scared about sending the wrong message. It has to be they want to send the message 14. So they encrypt it by doing 14 to the 27th power mod 55, which I'll do over here. So they do 14 to the 27th power mod 55. Whoops. 14 to the 27th power mod 55. Out comes the number 9. They send that number to Alice. Now Alice's private key is going to be also 55. Is it 4? Let's see. We have to get a number. We have to solve 27D. Oh yes, is equal to, yes, phi of 55. Since 55 is 5 times 11, is going to be 4 times 10, which is 40. So Alice needs to figure out what number can you multiply 27 by to get one more than a multiple of 40. Here you can, it's a small number. It is 3. 3 times 27 is 81. So D equals 3. So according to this, Alice should be able to decrypt that 9 by raising 9 to the 3rd power and modding it by 55. Oh yeah, small enough that so she takes her encrypted message, raises it to her secret key, and mods it by 55. Out comes the original message, which was 14. So as you can see, this is all based on the fact that it's difficult, maybe impossible, to factor a giant 200-digit number. If you could factor it, you can get their secret key from them. All the information. It's very funny because all the information is located right here. We're daring them to crack our number. And for a while, they used to have something called the RSA challenge, where they put up a 200-digit number and say, whoever can factor this gets $20,000. And it was, you set your computer and just try to do it. But they stopped doing it. People are getting better at factoring. One day, factoring might become a trivial problem, in which case they're going to need better encryption schemes. So now that you know the basics behind RSA encryption, maybe you could be the people. You get very rich. RSA, Rivis, Shamir, and Edelman are very, very rich men because they have a copyright on this RSA encryption. And so you have to know the old stuff before you could invent the next one. Okay, so oh, there's a question? Yes?
Which is the original two numbers?
Oh, the P and Q? Those are 5 and 11. So you pick 2 random prime numbers to begin with. You pick them. You pick you can make a computer program to randomly create prime numbers pretty easily, but those are just picked at random. Okay, everybody, I'm going to try to post this up on YouTube for you. Thanks a lot.